Okay, so today I'm going to be making a video about the different, why can't I think of the word? It's about carboxylic acid derivatives. I don't know why I just forgot that. About carboxylic acid derivatives, and this is actually one of my favorite things to do, and I'm actually pretty excited about it. So, yeah, let's talk about it. So first, I think we need to start with the understanding the reactivity of carboxylic acid derivatives. And let me flip to this page in my notes here. I just want to make sure I get everything right. So there are a number of carboxylic acid derivatives. There is what's known as an acid chloride. You've probably also recognized this as an acyl group in your Friedel-Crafts acylation reaction. This is an acid anhydride. We have an ester. And an amide. It could be NH2, NR2, or whatever. So these are the main derivatives. This is acid chloride. We have acid anhydride, and these are called acid, even though they aren't acids, because they are derivatives of carboxylic acids. So if you take away the OH, you get the chlorine there. And on this one, if you took away a hydrogen, anhydride, you would get from the carboxylic acid, you get that acid anhydride. So you take away a hydrogen from one carboxylic acid and OH from the other, that's a water anhydride. Okay, so these are some of the big derivatives of carboxylic acid. And what's interesting about these is they actually are decreasing reactive. Like this is the most reactive. And you can turn this into the most other things, but the amides are the least reactive. They don't turn into very much. But because you have the ability, pretty frequently in carbonyl chemistry we've seen this a lot. If you have a good leaving group and a nucleophile attacks, it can come attack and kick up, and you'll get your O- with your leaving group and your nucleophile, and then this will recover and kick out, and you get this. You can actually pretty easily go from an acid chloride to an acid anhydride. If you have an acid chloride and you have like a deprotonated carboxylic acid, it can attack, kick up, and do the whole thing. You'd get O- with O, and your leaving group is your chlorine, and this will come back down and kick it up, and you get an acid anhydride. So you can do that same thing if you have an acid chloride and you want an ester, or if you have an acid chloride and you want an amide. But you can't go backwards. So you can go this way, and you can turn anything here to something further to the right on the list, right? Like we can go from an acid chloride to an acid anhydride, an acid chloride to an ester, an acid anhydride to an ester, an acid anhydride to an amide. We can go from an ester to an amide, but we can't actually turn an amide into an ester, an amide into an anhydride, or an amide into an acid chloride, because the reactivity of that isn't good. This would predominate if you put this in with like an alcohol to attack. This is going to be the main thing that predominates based on the way the equilibrium would lie. So you can go this way, but you can't go the other way. And what I want to do actually to kind of demonstrate that is make a big group of reactions. So I'm going to do it on separate pages, but I'm going to do 4 charts. So we'll have the acid chloride, we'll have the acid anhydride, and I'm going to try to keep them separate if I can remember. And this is just any R. It's not just a methyl. Any R group will work this way. An ester, and the amide. And for each of these, we're going to talk about what you need to make this and then what you can turn this into. So what do you need to make this and what do you need to what can you react this forward with? What do you need to make this and what can you react this forward with? And we're going to do that for every single one of these, and we'll get several big charts of this, basically 4 separate pages of this. And this has been like one of the number one things that's kind of helped me organize carboxylic acid derivatives in my mind. So we're going to start with making an acid chloride, and we'll be able to turn it into all these things, and then we'll be able to do a few other things. So an acid chloride, hopefully you already know one way that you can make an acid chloride, and that's if you start with carboxylic acid and you react it with SOCl3. But also I'm going to add PCl3 and PCl5. All those will do the same thing. So any of those will make an acid chloride. So you need to be able to recognize these reagents and know what they'll do. And then you can react an acid chloride with almost anything and it will make almost anything. So if you react an acid chloride with an alcohol, this would be your nucleophile. It would come in an attack, kick this up, your leaving group would leave, and it would have to get deprotonated, and you'd make an ester. If you react your acid chloride with, I already actually showed this reaction, but with a carboxylate salt, O-, you'll get an acid anhydride. Uh-oh, I lost my green pen. Here it is. If you react acid chloride with an amine, you will get an amide. It should be an R2. It could be 3 H's or whatever. It just needs at least 1 hydrogen there. You'll get an amide. And then there's a few other things that you can do with this. Typically, if you have any carboxylic acid derivative and you react it with water and acid, or water and base, it will go back to being the carboxylic acid. Of course, if you have carboxylic acid in basic conditions, it'll be the carboxylate salt. So you'd need to protonate it afterwards. But if you did it with base, it'll go to O-. If you do it with acid, it'll go to OH because these reactions are reversible. And then the only other thing is if you react this with anything you knew previously. So I'm not going to include this on your current chart, but you should recognize this as a Friedel-Crafts acylation reagent, right? So if you have this with the benzene ring and AlCl3, you can make you can substitute, I don't know what's happening to my brain today, a benzene ring with an acyl group. So this is your overall acid chloride chart. And we saw on this chart that just by having these nucleophiles that attack, come back, this recovers, and the leaving group leaves, you can substitute this chlorine out for OH, for an acid anhydride, for an amide, for back to OH, or back to O-, a carboxylate salt. So you could do any of these. We went from acid chloride to acid anhydride to ester and to amide. Okay, so now let's look at acid anhydrides. So you just learned one way to make an acid anhydride. So let's start with that. If we're going to make acid anhydrides, we know that way. We can react an acid chloride with a carboxylate salt, and you can make a carboxylate salt by reacting an acid chloride or any other carboxylic acid derivative with sodium hydroxide and water. That's the only way I know of to make an acid anhydride for y'all at this point. The only other thing would be maybe, no, that wouldn't work. So yeah, that's the only way I know at this point. And then you can turn this into an ester or an amide by doing the same thing, but you cannot use chlorine as a nucleophile to attack and substitute out. So you can't turn it back into an acid chloride, but you can turn it into an ester if you react it with an alcohol. You'll get an ester. So the nucleophile will come in and attack right here, kick up, come down, and this whole thing is a good leaving group, so it'll leave, or a good enough leaving group. If you react it with R2NH, same as the other one, this nitrogen will come attack, kick up. And in both of these cases, they do have to be deprotonated, but the big thing is this group, this OR, this NR2 will be substituted out for this whole leaving group here, and you'll get NR2. So we've got our ester formed, and we have our amide formed. And then the other thing you can do with any carboxylic acid derivative is with water and acid, or with OH minus and water, you can turn it back into what it was before. So you can turn it back into the carboxylic acid, or you can turn it back into O minus with the base, because if you have carboxylic acid in the presence of base, it's going to deprotonate it. So that's the big thing with these. I will say, because this is your leaving group in this case, which is kind of different than some of the other ones, you'll also get the product of this leaving. So, you'll get something like this on each one. But usually we're focused on the major product. So we don't worry too much about the this carboxylate salt that also is forming, but it does also form. And the same thing is actually true here. I mean, you'll also get your, Cl minus, because that's your leaving group, but we don't worry too much about that. Okay, so let's go back to our overview here. We turned an acid chloride into acid anhydride, ester, and amide, and we turned an acid anhydride into an ester and an amide, but we cannot turn an acid anhydride back to an acid chloride. So the next thing we'll do is we're going to use the same reagents to do the same thing. So I really want to draw your attention to that here as well. We've used alcohol to turn both of these leaving groups. We basically swapped out the Cl for the OR, and then it got deprotonated. We swapped out this leaving group for the OR, and then, again, that has to get deprotonated. Or we used an amine to swap out the leaving group for NH2 or NR2 in both of these cases. So you're using the same nucleophile to swap out for a leaving group. You just have to know that you have to follow this order of reactivity for that reaction to proceed successfully. Okay, so the next thing is an ester. So you actually know a few ways to make an ester. We went over two of them already. One is to react an acid chloride. One is to react an acid anhydride. So let's go ahead and put those on there. An acid chloride with an alcohol. An acid anhydride with an alcohol. I'm going to make this R, and we'll make the one that's being substituted out as R prime. So this is your existing R, and then we have R prime. You also learned that you could do carboxylic acid with alcohol. We learned that in an earlier chapter. I think it was that chapter 11 maybe. I'm not 100% sure. And you learned Baeyer-Villiger oxidation. So MCPBA or anything else would add an oxygen, in between the two. So MCPBA or any other peroxy acid will add an oxygen there. So these are all the ways to make an ester. There's also Fischer esterification, I think you learned. This might be Fischer esterification. I can't remember the names of all the reactions. I think these are the major ones. If there's one I forgot, this is a good opportunity for you to go back and review for your final anyway. And because there's only one other thing on the list here, the only other carboxylic acid derivative we can easily turn this into is an amide. So if you react this with HR2N or any amine with at least one hydrogen, you'll get your amide. And then you can do the same thing if you do H plus in water, or if you do OH minus in water, you will get O minus, or you'll get your carboxylic acid. That's the only carboxylic acid derivative, though, that you can turn an ester into is an amide. You can't go back to any of these others. Chlorine's not a strong enough nucleophile. Your carboxylate salt's not good enough. So you have to only use these to be able to, the only thing you can do is basically turn this into an amine. So we've now gone through and done acid chloride into anhydride, anhydride into ester, and now we're going to do, we did ester into amide, and now we're going to do amide. Amides are the least reactive, so they really make the least things, actually. So amides, you've learned a few different ways to make them. You learned with acid chloride, with acid anhydride. I don't know why I drew that like that. With ester. And with carboxylic acid. All of these. And you use the same reagent for all of these. R2NH, 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 and you get an amide for all of these. We'll say this is R, and this is R prime. So all these make an amide, and they all go through the same way, right? So, and again, I just want to draw your attention to that. The same thing in ester. It's like all these make an ester. You just use alcohol on any carboxylic acid derivative to turn it into an ester, except an amide. You just use a carboxylate salt on chlorine to turn it into an acid anhydride. So for amides, we then can react those forward in only a few ways. They're the least reactive again, so they'll be able to do the same thing with water and acid or water and base. And then there's one special reaction that this one can do that nothing else can do. With acid, it'll be OH. With base, it'll be O minus. And then if you have, this is like so weird, you do not need to know how this happens. But if you have P4O10, it will convert it to, it converts this carbon right here into a nitrogen. So it gets rid basically of this and turns this into a carbon-carbon triple bond. But that nitrogen's fully formed, so you also lose these. Basically, this is what's left, and this turns into a carbon-carbon triple bond. I don't know if Dr. Krauss will test you over this. It sometimes comes up with other professors. But yeah, so this is just an overview of the reactions of carboxylic acid derivatives. I honestly think that this is pretty satisfying and also kind of like, I don't want to say easy because it's organic chemistry, so it's not easy, right? But it's like you're using the same nucleophile every time, as long as you know you can go this way, you can't go this way. So if I want to turn an acid chloride into anything, I just use the nucleophilic version of this, or this, or this, right? And if I want to turn an acid anhydride into anything, I can't go backwards, but I can use the nucleophilic version of this or this. So, that works. Or if I want to turn an ester into anything, well, I'm only going to be able to really turn it into an amide or back to a carboxylic acid. And so I'll use the nucleophilic version of this, an NH2, right? So you use the same reagents every time, and you get the same results every time. And so for me, there's like some satisfaction in the pattern of that and how organized that is. So again, just to go over it one more time, to turn a carboxylic acid into an acid chloride, you use SOCl3 or PCl3 or PCl5. And then Alcohols make esters, carboxylate salts make anhydrides, amine makes amides. And then you can always, this is called hydrolyze back to its original state. And then here we have an acid chloride reacting with a carboxylate salt to make an anhydride. And then the same thing, alcohols make esters, only if it's not an amine. Amines make amides, and then you can hydrolyze it back to its original state. And then here's all the ways that we've already learned to make an ester. So with an alcohol for an acid chloride, an alcohol for an acid anhydride, and then you learned these previously. And then again, an amine makes an amide, and we can hydrolyze it back to its original state. And then last but not least, here's all the ways we learned. You can add an amine to any of these things. So it's the same reagent every time to get an amide, and you can hydrolyze the amide back, and then there's a special reaction to turn this into a cyano group. So I think that this is a really good overview of everything pretty much that you learn in chapter 17. This to me is like one of the most satisfying videos. So I hope that was helpful to you. And if you have any questions, please feel free to reach out.